In the name of God, hello dear students, my name is Masood, I'm a physics teacher. So far we took about this chapter 2, we entered chapter 2 and we solved some questions, but we didn't finish it. Right now we want to move to another question, which is question number 8, and it talks about, let's say, difference between two types of gases, ordinary gases and inert gases. Let me read the question for you. Question number 8, distinguish between ordinary gases and inert gases, right? This is the answer. Let's say, answered it in a table, right? Answered it in a table for better understanding. Ordinary gases, number 1, the first difference, they are elements made of many atoms. They are made of many atoms, right? The first difference here, let's say for ordinary gas, I read it for you. Right now for this one, for the inert gas, or I can say noble gases. If you say inert gas or noble gas, it doesn't matter, as you like. They are elements made of individual atoms. You see, here atoms made of many atoms, like what? Here elements made of many atoms, like what? Like oxygen, for example. Right? This is the chemical formula of oxygen. I wrote it, let's say, in pairs. Yeah? What else? We have nitrogen. Let's say I write it in pairs, right? We have, for example, oxygen, nitrogen, hydrogen, right? About the inert gases or noble gases, they are elements made of individual atoms, like what? Like helium, right? Helium, neon. You see, I don't put any subscript here. I just write the element, right? Without any subscript. He means helium, neon, xenon, krypton, right? And so on. So they are inert gases or noble gases. Let's say they are found in nature individually, right? They don't, let's say, move in pairs, but ordinary gases in nature move in pairs, like oxygen, nitrogen, hydrogen, so on. The second difference, ordinary gases, there is a chemical bond. There's a chemical bond between any two atoms. So atoms are dependent. They bind, let's say, with one another by bond, right? What do you say about inert gases? Do inert gases make bond or not? Let's read it. There is no chemical bond. There is no chemical bond between the atoms, right? Atoms are independent. Atoms are independent. They move separately, so they cannot, let's say, they are not able to make bonds. The third difference about the ordinary gases, their atoms move in pairs. Yeah, I told you actually. The atoms move in pairs or they form molecules. I told you about molecules. Molecules means one molecule consists of two or more atoms, right? Two or more atom, collection of two or more atoms is called molecule. So ordinary gases make molecule, but inert gases or noble gases are not able to form molecule because they move individually, separately. They are, let's say, free, let's say, to move, and they don't, let's say, make bond between each other. Their atoms move individually. They do not form molecules, right? They do not form molecules. Number 4, the fourth, let's say, difference, they are chemically active. Ordinary gases are chemically active. What do I mean by this? Means they take part in chemical reactions. They participate in chemical reactions. But inert gases, they are not, let's say, they are not active. They are chemically inactive. Means they don't participate in chemical reactions. They are lazy. That's why they are. So these four differences are difference between ordinary gases and inert gases, right? Let's move on to another title. We have a new title here, the interatomic forces, right? interatomic force. What's the interatomic forces actually? Interatomic forces means actually a pair of force that exists simultaneously between the, let's say, atoms of matter, right? It's a pair of force actually. A pair of forces acts on the atoms simultaneously. You see, at the same time, they appear. They compete with one another. Sometimes they cancel one another, especially in normal situation, under the normal pressure and in at let's say normal temperature. They cancel one another, but sometimes one of them overcomes the other and dominates over the other, right? Let me read the definition, let's say, for you. The interatomic forces, a pair of forces acts on the atoms simultaneously that gives rise to what? That gives rise to hold the matter together. So interatomic force holds the matter. Interatomic forces hold the matter together, right? They let's say they are in charge of what? They are in charge of, let's say, giving the matter a certain face, right? That's why this is the function of interatomic forces. And in general, there are two types of interatomic forces: attractive force and repulsive force. Types of interatomic forces actually. Attractive force appears between unlike charges, like what? Like let's say unlike charges means, for example, unlike means positive and negative. Between proton and electron, we have attraction, right? They attract one another. Between, so repulsive force appears between like charges. Like charges means proton with proton, electron with electron, right? Nucleus with nucleus, because nucleus carries positive charge, and we can say electron clouds with electron clouds, they repel one another, right? And you know what electron cloud is? Electron clouds means outermost layer or outermost shell of the atom, which is full of electrons, or sometimes, let's say, partially filled actually. It's not completely full. So this is called electron cloud actually. And this is interatomic force. Let's move on to another. I think we have some notes here. Let me read it for you. Or we have another title: equilibrium distance. This is the symbol of equilibrium distance. R naught is the equilibrium distance. So what's the equilibrium distance? Let me read the definition for you, and after that I'll explain it for you. It says the average distance between two neighboring atoms in which the net force becomes zero. It means force of attraction balances force of repulsion, so summation of forces becomes zero. This is called, let's say, equilibrium distance, or R naught. What's the equilibrium distance? The average distance or minimum distance between two neighboring atoms in which the summation of forces becomes zero. What do I mean by this summation of forces? I mean summation of interatomic forces becomes zero. It means attractive force balances, let's say, repulsive force. No one overcomes the other. They completely cancel one another. That's why we have this situation in normal situation. I told you, at normal temperature under the normal pressure. We have a note here. It says, in normal situation, there exist two forces between any two atoms of an element simultaneously, right? At the same time. What are these forces? Go over it, think about it. Either we have attraction and let's say, or repulsion, or I can say, because I say simultaneously, you have to say we have attraction and repulsion, which are equal. You see, I wrote it in bold. I wrote this in bold. These forces are equal in magnitude and opposite in direction. That's why they cancel one another, right? Symbolically, I can say attractive force is equal to repulsive force, which leads to what? Which leads to sigma F is equal to 0, means summation of forces becomes 0. This state is called equilibrium state. So what's the equilibrium state? Means the state in which the interatomic forces balance one another, right? No one overcomes the other, summation of forces becomes 0, and that's it, right? Let me read the, let's move to another subject. So I prepared the table for you for better understanding. We have a table. Let me read the table for you. Actually, interatomic distance, we have some cases actually. We have 3 cases here. Either we have this, the first case. Let me, let's say, we have the first case, number 1. Either we have R is equal to R naught. R means interatomic distance, R, right? R is interatomic. If interatomic distance means distance between 2 neighboring atoms, let's say is equal to R naught. So at what situation we have this, let's say this condition actually, in this situation we have interatomic force. If R is equal to R naught, if it's force of attraction balances force of repulsion, and I can say sigma F becomes 0, and the change in potential energy becomes 0. And what's the description? Description of the first case. You can describe it like this. Number 1, no force appears. I told you no one overcomes the other, right? Number 2, equilibrium state is achieved. Equilibrium state is achieved, right? Let me, let's say, draw it for you for better understanding. For example, they are what? They are neighboring atoms, right? What's this? This is R naught. This is R naught. Average distance between 2 neighboring atoms within the material. This is called R naught or equilibrium distance. If material remains as it is, actually, I told you no force appears here, as if there is no force. Actually, there exists force. There exist forces actually here, but they cancel one another as if there is no force, right? Simultaneously, they attract one another and they repel one another. That's why, because these forces are equal in magnitude and opposite in direction, that's why they, let's say, they cancel one another, right? Let's move on to another case, another one. The second case, we have a condition if R is greater than R naught, right? If R is greater than R naught, this is the second case. Let me erase this one. If R is equal to R naught, this is the second case, right? Number 2. What's the meaning of this? If R is equal to R is greater than R naught, means atoms, let's say, spread apart. They spread apart. They spread away from one another, and I can say R approaches infinity. I told you this is the normal situation, and I can say this is R naught, yeah, right? R naught. Equilibrium distance, right? Is it our case? No, because it says R is greater than R naught. Let's say atoms spread apart more than equilibrium distance, like what? Like this. So this is our case. In this situation, I can say R is greater than R naught. What thing happens here, right? So force of attraction overcomes force of repulsion. Force of attraction, this force of attraction, right? Force of attraction tries to, let's say, bring the atoms to the what? To the equilibrium distance. It tries to bring the matter into the original situation. This is the role of force of attraction here, and it's larger than force of repulsion. It wins the, let's say, battle here. It overcomes the force of repulsion. So what's this? This is the, let me write it here. This is sigma F, right? or summation of forces. Summation of forces is negative, right? If summation of forces is negative, means force of attraction overcomes force of repulsion. Keep in mind, right? Here we have delta PE. Delta PE means change in potential energy. And whenever force of attraction overcomes force of repulsion, means change in potential energy is negative, right? Keep it in your mind. Both of, let's say, sigma F and delta PE becomes negative. At what situation? When force of attraction is greater than force of repulsion. So when do we have this situation? When R is greater than R naught. When atoms, let's say, separate, let's say, from one another, when they move away from one another more than the, let's say, equilibrium distance, right? So let me explain delta PE, let's say, for you, for better understanding. Why do we say delta P is negative? Because look here, this is the, let's say, the first case of us, right? Because it says R is greater than R naught. Atoms right now in this situation, atoms right now are in this situation. R is greater than, this is the first, let's say, or initial, let me write it. This is the initial position of atoms, right? They are moved away from one another, right? So I told you in this situation, force of attraction, let's say, appears and tries to what? And tries to bring the material into its, let's say, equilibrium distance. So atoms move from what? Atoms move from larger distances to smaller distances. Larger distance to a smaller distance means distance decreases. And distance is a measure of potential energy. Whenever distance decreases means potential energy decreases, right? Maybe you say, teacher, what do you say about the kinetic energy? Kinetic energy is opposite to the potential energy. Here I said delta P is negative. You can say delta Ke is positive, right? Because kinetic energy and potential energy are inversely proportional to one another. They are, let's say, opposite to one another. Say when separation, when atomic separation is increased, what happens to the material? I can say weak and long range attraction force emerges. Why do we say long range attraction force? Because look here, because you see that the separation, let's say, atomic separation is what? Is greater than, let's say, is greater than equilibrium distance. That's why I say this is our situation, right? This is our case. So we have long range, yeah? Force, attraction force appears, let's say, in a long distances. That's why we have weak and long attraction force, long range attraction force appears, right? Between the neighboring atoms. What's the other consequence of this case actually? Chemical bonds are formed. So I told you attraction force or attractive force brings the material, let's say, to one another. It brings them to, let's say, it tries to bring them together, right? And tries to return the material into equilibrium position. That's why chemical bonds are formed, right? In this situation. Let's move on to another one, which is the last case actually. What happens to the material if the R is less than R naught? If R is less than R naught, actually, what happens to the material? What's this? Let me, let's say, draw a situation. This is R naught, right? R naught. But here it says R, or atomic separation, or atomic separation means R, yeah, right? Or I can say atomic distance, as you like. Atomic separation, atomic distance, no problem, as you like, doesn't matter. So this is R naught, right? But our case is what? Our case is R is less than R naught. Atoms are what? Atoms are very close to one another. So R is less than R naught. This is the first or initial case, right? Initial case. In this situation, what happens to these atoms? What are the reactions of these atoms? Which force appears between these neighboring atoms actually? Here, because equilibrium distances is collapsed, let's say. Then, let's say the atoms are about to touch one another. They are very close to one another. That's why force of repulsion, look here, force of repulsion, let's say, overcomes the, look here, force of repulsion overcomes the force of attraction. For which purpose? To, let's say, to bring the atoms into its original case, into its equilibrium case, let's say, right? So in the case of decreasing atomic separation, so repulsive force appears. Repulsion overcomes the attraction, right? For which purpose? What's the goal of this action actually? In order to bring the material to its equilibrium distance, right? What do you say about this sigma F actually? Summation of forces become positive. Keep it in your mind. Whenever repulsive force overcomes the attractive force, means we have positive sigma F, positive net force, right? What do you say about the change in potential energy? And change in potential energy is positive as well. Why? Because look here, let me explain for you. So I have a question for you, and I want you to be with me. Concentrate on this question. This is my question. Let's say what happens to the atoms? Do atoms move from the smaller distance to larger distance, or from larger distance to a smaller distance, right? Look here. I told you this is the first case of us because atoms are about to touch one another. This is the initial case, right? That's why in initial case we have a very small separation here, right? By means of repulsive force, they move away from one another, right? So look here. This is the initial case. This is the final case. Initial, final. So atoms move from small distances to large distances. So separation increases. Distance increases. And I told you, distance is a measure of potential energy. Because distance increases, that's why potential energy increases, or I can say delta P is positive, right? Teacher, what do you say about the kinetic energy? Change in kinetic energy is negative. Because I told you, potential energy and kinetic energy are reciprocal. They are opposite to one another. The one, for example, increases, the other decreases, and vice versa. So what's the consequence, or what's the description of matter in this situation? When R is, let's say, is very small, let's say to the extent that R approaches zero. What happens to the material? So if R is less than R naught, or R is about to, for example, to zero, right? A strong and short range repulsive force dominates. So repulsive is appears at short distances. That's why we say repulsive short range. And the repulsive short range means it appears at very small distances when the atoms are very close to one another. And the amount of this force is very strong, right? The second consequence, electron clouds repel each other. Electron clouds in this situation repel each other. So it's like this. Let me draw an electron cloud. This is the first atom, for example, and this is the electron cloud. I told you, electron cloud carries a negative charge, and this is the second atom. And this is the electron cloud of second atom. It carries negative charge as well. So negative versus negative. What happens to the, so which force appears here? I told you, this is the force of electrostatic, right? Electrostatic force. I can say like charges repel one another by a, let's say, repulsive force, right? And this is about, let's say, this example actually. Let me explain another one. Some tips about the table. I want to, let's say, read some tips about the table, right? The first tip actually, in the case of increasing atomic separation. What do I mean by this? Means if R is greater than R naught, what happens? Think about it. I explained it for you. So which force dominates without looking to the answer, actually? In the case of increasing atomic separation, I told you, let's say attractive force tends to bring the matter into the equilibrium position. That's why attractive force dominates over the repulsive force in order to what? In order to bring the atoms into equilibrium distance or R naught, right? That's the first tip. Another tip, in the case of decreasing atomic separation, what do I mean by this? Means if we have R is less than R naught, or I can say if R approaches zero, atoms are about to touch one another. In this situation, think about it without looking to the answer actually. I want you to go over it. In the case of decreasing atomic separation, repulsive force overcomes the situation. It, let's say, dominates over the attractive force, right? For which purpose? For the same purpose, in order to bring the material or return the material or atoms into the normal situation or equilibrium distance, right? We have another tip. Let me read it for you. Number 3, any change in potential energy of atom, right? Any change in potential energy within the atoms in a solid matter is reciprocal to the kinetic, to the change in kinetic energy. It means delta PE is reciprocal to the, let's say, delta KE. Means there's an inverse relationship between change in potential energy and change in kinetic energy. And I explained it for you actually, right? And we have a graph here. The graph talks about what? The graph talks about and the name of this graph or curve is the interatomic force distance curve. We have a curve here, or we have a graph. Let me, let's say, interpret the graph for you. The graph, let's say, focuses on what? It focuses on two things. It focuses on the interatomic force on the vertical axis and atomic separation on horizontal axis, right? The upper part, so F is equal to 0. What do I mean by this? Think about it. If I say F is equal to 0 means we have an equilibrium situation, right? The horizontal line means equilibrium position. Above the horizontal line or above the equilibrium position, we have positive repulsive force. You see positive repulsive force? Let me, so positive repulsive force act at what, let's say, distance, right? It acts at what distance, at what range? It acts as at a very short, let's say, distances, right? Repulsive force is positive, is a strong, and it acts at very short distance. That's why we say short range, strong force. So the upper part is dedicated for attractive force, right? Excuse me, repulsive force, repulsive. Horizontal line is dedicated for equilibrium position or equilibrium state. The lower part of the curve actually talks about what? The lower part talks about a negative attractive force, right? Which is which acts at which, let's say, distances. It acts at very long distances. That's why we say long range, let's say, weak attractive force. Upper part is dedicated for repulsive force and it's positive. It's short range force. Lower part is dedicated for attractive, it's negative, and it's a long range force. Equilibrium distance or equilibrium, let's say, state exactly lies at what? Exactly lies at equilibrium, lies at horizontal axis or x-axis, right? So we have this curve, right? We have this curve. I can say, I want you to think about the intersection of these curves actually at exactly this position. Could you tell me what this position is, right? What does it represent? So let's say repulsive force and attractive force intersect one another here. They intersect one another, and I told you, let's say horizontal axis is what? Horizontal axis mentions what? Mentions, let's say, zero net force. What do I mean by this? So intersection of upper part of the curve and the lower part of the curve indicates the R naught or equilibrium distance. That's it, right? Let's move on to the tip about this topic. Actually, this topic is very important and it's very easy, right? It's very easy. It's nothing, but it needs to actually practice. You have to practice a lot. You have to bring a paper and pen and practice it with your hand in order to better understanding the subject. So we have some tips here about the graph, right? About the curve. It says from the graph, attractive force emerges in very long distance. Let's say showed it to you on the graph actually. Let me just read the subject. I explained all of these information. It says from the graph, attractive force emerges in very long distances, more than equilibrium distance. Actually, it means R is greater than R naught. R is greater than R naught. This one. Therefore, it's called weak and long range force. The second tip, repulsive force appears in very short distances, less than equilibrium distance. What do I mean by this? Means R is less than R naught. Therefore, it's called strong and short range force. And the third tip, finally, when upper, look here, I explained it for when upper and lower part of the curve meet with one another, they intersect each other, right? Equilibrium distance is achieved, means R is equal to R naught, right? We have some questions about we have some questions. Let me read the question for you. Question number 1 about this subject actually. It has to do with our subject. It has to do with interatomic force and interatomic, let's say, distances. It says compare solids, liquids, and gases based on what? Based on some, let's say, some quantities. Based on interatomic attractive force, right? Whether it's high or low. Based on equilibrium distances, whether it's equilibrium distance high or low or nothing, maybe, or let's say balance. I'm talking about, let's say, all situation. Number 3, particles motion, right? I answered this question by a table for better understanding, for simplifying the case actually. So we have 3 things. Yeah? We have 3 factors. We want to compare 3 phases, solid, liquid, and gases, based on what? Attractive force among the atoms or interatomic forces, especially attractive. It mentions attractive, no problem. We focus on attractive forces, right? We focus on attractive force, equilibrium distance, R naught, particles motion. Look here, in solid, it's very important. If you understood the subject, you can, let's say, fill this table. Firstly, solid, right? Attractive force between the atoms of solid. Guess let's say, the value of the attractive force between the solids. I told you, in solids are about to touch one another. Particles of solid, they are very close to one another. They are about to touch one another. This is R naught, right? So in this situation, attractive force between these, let's say, how do, let's say, these atoms sit beside one another? By means of attractive force, actually. Attractive force are in charge of bring the materials, bring the atoms, let's say, to one another, right? So attractive force is very strong in solids, very strong. I don't say strong, it's very strong, extremely strong. What do you say about equilibrium distance? You see, equilibrium distance is nothing, let's say. It's very, very, very little, actually, very small. What do you say about particles' motion? Whenever you have this situation, the particles are very close to one another. That's why they are not allowed to move freely. They have, let's say, motion, no problem, but they just jiggle, actually. They just vibrate up and down. They just move up and down. So they are not freely, let's say, moving. So particles motion is very slow. So means we have vibration. So vibration is what? Vibration is a feature of solid, actually. Solid is famous for vibration, right? So atoms within the solid, let's say, vibrate, right? So they have a very small, let's say, motion. That's why they have a certain shape, actually, because the motion is very limited, is very restricted, actually. What do you say about the liquid? Liquid, attractive force between the liquids are very close to solids in some features, like, let's say. So here I can say equilibrium distance is liquid is a little bit more than the equilibrium distance in solid. It's a little bit, let's say, more than this. It's very close to solid in traits, actually. Liquids are very close to solids in properties. That's why here attractive force is strong. What is about equilibrium distance? We have a small equilibrium distance here. Atomic separation is very small. I just say very small. This is small, right? These terms are very accurate. You have to, let's say, memorize it as it is. Particles motion. So what do you think about the particles motion of, for example, liquid? They are relatively fast. So they have circulation. They circulate, right? They circulate within the matter. That's why they are relatively fast. I don't say very fast. They are relatively fast. And liquids are very close to solid. Let me give you an example about the solid and liquid. And I want to, let's say, tell about for example, glass. Yeah, glass is called, let's say, exceptional liquid. Glass, and glass is solid, right? This glass, for example, is solid, but it's called sometimes, we can call it sometimes exceptional liquid. Why? Because of the let's say arrangement, because of the arrangement of array of particles. Because here in solid we don't have, let's say, uniform pattern for let's say for atoms. That's why this is solid, and it's very close to the one. It's very close to liquid. That's why I told you liquids and solid are, let's say, are very let's say close to one another in properties. About the gas, actually, about the gas state, attractive force between the gas state. Look here. Let me draw two neighboring atoms of gas state. Look here. You see, there's a big gap between two neighboring atoms of gas state. This is R naught. So they are very, very, let's say, far away from one another. That's why there's a very weak attractive force between the neighboring atoms, right? Very weak, right? Equilibrium distances, I told you, equilibrium distances, they are very, very large, right? Particles motion, because because atoms are very, let's say, far away from one another. That's why they can move freely, right? They can move freely, and the motion, description of motion, we say they are very fast, or they have rapid motion. Rapid motion is let's say, so gases are famous for what? Gases are famous for rapid motion. Liquids are famous for circulation. Solids are famous for vibration. Memorize these, let's say, terms, and that's all for today. I appreciate you to watch this video. I want you to follow the next videos, and take care.